Greetings and salutations, magical chemists. Today we're going to talk a little bit more about equilibrium, more specifically about the reaction quotient, Q. Q is what you use when you need to know the answer to the question, is the system at equilibrium? Well, the answer could be yes or no. If you look at how we write the expression for Q, it might look kind of familiar. You might be thinking, wait, isn't that how we write out the expression for K? Well, yeah, actually, it's exactly the same way we write it. But here's the thing. It looks like K, but if you're writing an expression for Q, it means that the concentrations you're plugging in are not necessarily at equilibrium. Either you know for sure it's not at equilibrium, or you honestly don't know. So, K is a constant at room temperature, but Q can change. The reason we calculate Q is because you can determine by comparing Q to K whether or not the reaction is going to have to make more products to reach equilibrium or make more reactants, or if in fact it already was at equilibrium all along. There is an amazing trick that will always help you remember which way to determine that reaction is going to shift, is if you put K and Q in alphabetical order when you numerically compare them. The reason that's so important, well, okay, let's see what happens if K is bigger than Q. Well, the system's not at equilibrium because they're not the same. And the best part about this, you can use that greater than sign and you turn it into an arrow pointing in the direction the reaction is going to go. In this case, because K is bigger than Q, you don't have enough products, so the system is going to shift forward. Basically, the forward reaction is going to happen, making more products to make Q equal to K. So when we use the phrase shifting right, the reaction is going to shift right, that just literally means some of your reactants are going to convert into products. Okay, now of course, if K is equal to Q, then you are at equilibrium and nothing's going to change. And if K is less than Q, well, the system's not at equilibrium and the reverse reaction is favored. And that means the reaction is going to have to shift left or convert some of its products into reactants to reach equilibrium and make Q equals K. So there's a lot of weird language that comes up with equilibrium, so I wanted to make sure you were aware of all the different ways we could say, well, this one thing that means the same thing. Yes, I know it's redundant, but it is what it is. Okay, so when we're talking about reaction shift, there's two different things to talk about. First, there's the situation where you need more products to be at equilibrium. This is when K is greater than Q. So we could say that the reaction will shift right, or instead of saying shift right, we could say, well, the forward reaction is occurring more rapidly, right? That's what shifting right means. You're making products at a faster rate than you're making reactants. Or you could just say, well, it's going to shift to make more products. Or you could just say it will proceed to the right. All of these things mean the same thing. And, the other way around. If we need more reactants to reach equilibrium, in that case, K is less than Q. So we could talk about how the reaction will shift left, or how the reverse reaction is going to occur more rapidly because we need to basically make more reactants. Or we're going to say it's going to shift to make more reactants, or it will proceed to the left. Again, all of these things mean the same thing, but you have to recognize all of them when you see them. Okay, let's go ahead and just try two practice problems so you can see how we use this reaction quotient Q in an actual problem. Okay, for number one, we're talking again about the synthesis of ammonia. It's a very useful equation. And they tell you at a given temperature, the equilibrium constant, aka the value for K, is 6 times 10 to the negative 2. Well, they want to know, okay, well, that's great. What direction is the reaction going to shift to reach equilibrium if it's starting from these given concentrations? Well, notice it's talking about shift, which means you're not at equilibrium. That's when your brain needs to go, Q, I have to calculate Q. Luckily, calculating Q is just like calculating K. You're plugging into the Q expression. Before you plug in numbers, actually write the ratio for Q first. We've actually already written this expression for this equation. It was a K expression at the time, but it looks the same. It's still the products raised to their coefficients divided by reactants raised to their coefficients. And now we're going to plug in all the values that we have. And then, of course, we get to use our delicious calculator. And then you get a pretty dang big number, 1.3 times 10 to the 7th. Well, remember our value for K was actually a small number, so Q is bigger than K. But be careful when predicting your direction of shift. When predicting the direction of shift, we always want to write it in alpha order. Well, since Q is greater than K, that means K is less than Q. Since we wrote it in alpha order, that means we can use that less than sign as an arrow, showing that this reaction is going to have to shift left to reach equilibrium by increasing the concentration of reactants and decreasing the concentration of products. In a free response problem, when you have to explain yourself, you have to be pretty explicit. So we have to say it's going to shift left to reach equilibrium. And then you have to say why shifting left reaches equilibrium. Well, it'll reach equilibrium because you'll increase the amount of reactants or decrease the amount of products. Those are both equally correct. So make sure your answers are explicit when you're explaining this in free response. Hey, guess what? There's a second one that you're going to try, and it'll be ever so much fun. So you try it, pause the video, and when you're ready to check your answer, unpause the video. So first, of course, we have to calculate our value for Q, which is 670. And then we're going to compare that to the provided number for K. K, of course, is 2.4 times 10 to the third. That's just 2,400. So in our case, Q is definitely less than K. Now this problem was a little bit different because it actually asks you, is the system at equilibrium? Well, the values aren't equal, so it's definitely not at equilibrium, and it will need to shift right to achieve equilibrium by increasing the amount of products. And there you have it. That's K versus Q in a nutshell. So thank you, magical chemists, for playing with all of the glories of equilibrium.